to look at today, and this is the IR2153. Looks like there are two different models of it. We'll take a look at that later. And this is a self-oscillating half-bridge driver IC. I've been using this for a few days now to make an electronic speed controller for a brushless DC motor. And it's interesting the way we set it up. It also has another cousin that I think is the 2101 or something like that. Anyway, let's focus on this. This one features an integrated 600 volt half bridge gate driver. We're definitely not going to go to 600 volts. Maximum will be about 12 to 24 volts. It has a CT and RT programmable oscillator, and this is for the timing. You have a certain capacitor value with a certain resistor value that will tell you how fast in frequency the switching will be. 15.4 volt Zener clamp on VCC, micro power startup, non-latched shutdown on CT pin, which is a sixth of VCC, internal bootstrap FET. The bootstrap FET is something very important. We will talk about that in a bit. Excellent latch immunity on all inputs and outputs, blah, blah, blah. Internal dead time. So the main things that I would focus on in terms of its features, have a fancy little fountain pen over here, would be the internal dead time, the CT and RT values, and the internal bootstrap FET. Those are the three things that are important. What's nice is that its configuration with the capacitor and resistor is nifty, it's simple. And the internal bootstrap FET, this will let something start up when it cannot start up on its own. It gives it an additional push. It's like you're strapping your boot up, so it will provide it with the power that it cannot produce by itself to operate in the proper region. So that's what the bootstrap is all about. And the internal dead time is going to be very important. So let's take a look at first. Okay, so first of all, this is the wiring diagram. We have, forget these two. We have the positive coming in, and we have the first pin is the VCC, and we have the VB, which would be the V boot for bootstrap, the VS, this one I had connected to ground, and we have the COM, which is ground, and we have the part where the resistor value is and where the capacitor value is. And then we have the high waveform, which will be produced from pin number 7, which is high output, and the low output, which would be down like that, the negative for low output. So this one, if we had to draw like a reference line for it, this would be like this, and for the high, it would be like that. So this is the signal that we are delivering to the gate of the Mosfets. This one's going to receive the low signal, and this is going to receive the high signal. And the thing that we need to take care of, which is the internal dead time, is that we cannot have these two overlapping on each other. So we cannot have, if it's turning on like this, I cannot have it turning off right over here in sync, because that will make a conflict. I need some dead time between them to give it sort of, so that they don't overlap on one another. And so when we put these two in this configuration, their common output will go into the inductor and then the resistive load. This is the part that would be the motor's coil that we are exciting. The wiring that I did, I put a diode as well over here, bootstrap diode, to help these two behave correctly. And the IC, there are two. There's the one that is the surface mounted one and the through hole one. I have the through hole one, didn't get the surface mounted one, but it's the exact same thing. So that's the basic diagram that we will follow. If we want to take a look at some of the characteristics, the VB, which is the high side floating supply voltage, the maximum is 625 volts, minimum is minus 0.3. VS, high side floating supply offset voltage, is VB plus 0.3. We're not going to be in anywhere close to this. We're going to be a lot less, so we're safe. The voltage high output voltage, minimum is V supply minus 0.3 and VB plus 0.3, so we are all in the safe range. Milliampere, the supply current, we can only give it 25 milliampere, so we're safe. We're not going to be drawing that much current either way. These are the recommended operating conditions. So we have a high side floating voltage, VCC plus 0.7 for the V clamp diode, that's probably for the diode. Okay. Now what I found nicely presented, these components over here, which will be the RT and the CT, are mentioned over here, the recommended component values, which as RT and CT, timing resistor value, and CT pin capacitor value. Minimum 10 kilo ohms and minimum 330 picofarad. And over here, according to this graph, which I actually liked a lot, is you have the RT values, these values on top for the resistance in a logarithmic scale, and how it plays with the frequency. So for example, if over here I got a 100 ohm resistor and I went with a 10 nanofarad capacitor, that will give me just below 100, how many zeros is that? 1 million hertz frequency. So it depends on the resistor value, what I need and how fast I need the motor to go. I select the capacitor and the resistor values and the capacitor values, and I can see what's going on. In addition to that, these are the timing diagrams. So we have VCC when it reaches the V clamp, so it starts up. We have the R values and the capacitor values, and we can actually see the capacitor charging and discharging and the resistor. And so the output that is going to the gate of the Mosfets is going to be the low output and the high output, and we can see high, and when this is low, this is going to be high. So we are focusing over here. This is the low part and this is the high part, and we can see that we have this amount of dead time right over here, which is very important, so they are not overlapping. So you can see these squares are slightly smaller than this one. And then we have a 50% duty cycle, which I think they mentioned over here. Yes, duty cycle is 50%. And the driver source sink current 180 milliampere, V clamp 50, we saw that. The dead time is 1.1 microsecond, typical. And this is the version that I have, to 150 typical. Yeah, this is the version that I have. So I have 1.1 microsecond. So the other version, which is the IRS 21531D, that's faster, My one's just 1.1 microsecond, but it's not going to make a big difference in our DIY application. For other circuits, it might need to be a bit faster. So that is good. Did we miss anything? No. Yep, that's it. The last thing we have is the dead time waveform definition. RT, depending on the resistor, the resistor, 50% duty cycle over here, halfway up, and how it behaves with respect to the high output and the low output. All right, this is good. I'm gonna go wire it up, and we can take a look at how it behaves. All right, so we are now on the workshop bench, and we've wired everything up. This is the wiring. This is VCC pin number 1, and we have the bootstrap diode going to VB. We have a resistor. What's the value of this resistor? Let's measure it. I put the component values in a way that we can actually see the alternation. But if it was actually gonna be part of an ESC circuit, the motor would be going very slowly. So let's see the value of this resistor. We have this is about a 55 kilo ohm resistor. So we have a 55 kilo ohm resistor over here for RT, and for CT we have a 10 microfarad capacitor. So these are setting the timing, the switching timing, and this is for the startup, and that is 22 microfarad capacitor. Is it for the startup? Let me double check the data sheet. This is the capacitor, sorry, for the boot, for the bootstrap. That's that capacitor. So that's what that is. And we have pin number 7, which is going to be giving the high, and this one's going to be giving the low. So let's take a look at that when we hook it up to power. And we're going to supply it all with 12 volts. So what we should see is the high and the lows should be alternating, obviously. So we should see each of the LEDs exchanging turns. There we go. On, off, on, off, on, off. Let's hook up the oscilloscope and take a look at a few waveforms to see how they are behaving together. We hooked up the oscilloscope, and these are our waveforms apparently. Channel 1, which is this one, turning high, and the other one is turning low. If I remove this, I want to see how it behaves. So when we remove the capacitor, the C boot capacitor, this waveform went lower. If I put it back, hopefully in the right place now, my amplitude over here increased significantly. There's a big increase in that. If I go directly, that one is now 0. I'm gonna take a look at the individual pin of the output. I'm gonna probe right now pin number 5. That's pin number 5, given in blue. and pin number 5, 6, 7, pin number 7 is the one in yellow. So I'm curious as to why the pin number, which one was it? So you see how this pin is reading normally, but this pin is reading like a capacitive discharge. Oh no, it is reading correctly now. Okay, I think it might be the probe. It might be the probe, maybe the compensation on the probe. Anyway, they are giving the right waveform. This is the high, and then this is the low. It looks the same, but they're actually different because the LEDs are switching. You can actually speed up the switching if we get a potentiometer. Let me get a potentiometer and see how it changes behavior. So I hooked up a 10 kilo ohm potentiometer, and if I start to turn the knob, we can see how they are blinking much faster. To a degree, so it depends. So this is like the fastest, then slows down again. Probably because of the value of the resistor versus the charge and so on. Okay. Now what I'm going to do is continue the circuit and add two MOSFETs. Okay, so we added two MOSFETs so that we can take it one step at a time. First of all, we saw the high and the lows alternating, which means that they work just fine. That output is going to be fed. I'm going to put my hand over here. That output is going to turn this MOSFET on, these two alternatively, at the bases, which is pin number 1. The gate, sorry. The gate of the MOSFETs is pin number 1. Then we are going to connect the source of this to the drain of this. So when the current leaves this MOSFET, it powers this MOSFET, which is why we see the blinking light over here. This one's turning on, then this one's turning off, then on, off. They're alternating, just as the LEDs show. So in one way or another, the LEDs over here show how these two MOSFETs are turning on and off. And as a result of this high and low pattern, we can see how the LED is turning on and off. To make it even clearer, we can look at it under the oscilloscope. So we can take a look at, where's the oscilloscope? It's right there. Okay. We can take a look at one of the LEDs, how it's turning on and off and off and off. And then we can take a look at the LED that's next to it. Also how it's turning on and off and off and off. And then let us probe this LED. That's the final result of those two combined. How it's turning on and off, on and off. So that's very basic. That's it. This is the complete circuit over here. This is how it should behave. Now, of course, instead of this LED, which is just an indicator, you would have an inductor and a resistor. This would be acting as the motor. So you would have three of these if you have a three-phase brushless DC motor, and each one is going to be under a certain timing that's going to be switching every one of those three different coils at a different time.